Now let's do one example. We have a steam nozzle. The word steam tells us the working fluid is water, so make sure you choose the correct tables. P1 is given as 10 bar, T1 is 300 Celsius, and V1 is 30 meter per second. P2 is 1.5 bar, and T2 is 200 Celsius. Both P2 and T2 are smaller than P1 and T1. Why is that? Because if you want to increase the velocity, something else has to go down because energy is always conserved. So what goes down? Pressure and temperature. We know the system is at steady state and is adiabatic, meaning there's no heat transfer. The first part is to sketch the process 122S and 122 on a T versus S diagram. And the second part is to look for the efficiency of the nozzle. So let's sketch the diagram first. T versus S diagram. Here we have a vapor dome. And then just like before, let's sketch two constant pressure lines. Okay, which one will be P1 and which one will be P2? P1 is 10 bar and P2 is 1.5 bar. So P1 is bigger, so the top line should be P1. It's 10 bar. And the bottom one is P2, which is 1.5 bar. Next, we need to locate point number 1. In other words, you need to identify what is the phase of point number 1. How do we do that? We've done that several times now. We have P1 10 bar, we have T1 300 Celsius. That means we go to table A3. We start from pressure P1, which is 10 bar. And from the table, you can find the corresponding saturated temperature. We call T sat 1, and the value is 179.9 Celsius. Meanwhile, our actual temperature T1 is given as 300 Celsius, which is even higher than the saturated temperature. So the conclusion is point 1 must be superheated. Okay, so is that enough for us to fix number 1? Let's take a look. We know point 1 must be on P1 line, and also number 1 must be superheated. So can I put number 1 here? If I put number 1 here, where's number 2s? We know 1 to 2s, the letter S means isentropic. If the process is isentropic, entropy does not change. And entropy S is actually my x coordinate. So if your x coordinate does not change, it must be vertical line. So 1 to 2s must be a vertical line. If that's the case, 1 to 2s goes straight down. Number point 2s must be a mixture because it is within the dome. Second option, can I put number 1 here to the right a little bit so that when I go straight down, I end up at G point? Or option number 3, can I put number 1 further to the right and then when I go straight down, point 2s will end up as superheated water vapor. So all three solutions are possible at this moment. We need to identify which one is correct. How do we do that? We've done this once already. What we need is to find a reference line. And what is our reference line? Across this point. We call it point 2G. And what we do is to draw a reference line across this point. This is our reference line. And the x coordinate of this point is S2G. And in addition to S2G, you need to find S1. If S1 is less than S2G, you have to make sure you put number 1 to the left of this reference line. If S1 is greater than S2G, then you have to put number 1 to the right of this reference line. And if S1 is equal to S2G, then you have just to put number 1 right on this line. Okay, so we need to find S1 and S2G. Okay, so let's start from S1. How do we look for S1? Before you look for a property, you first have to identify the phase. And what is the phase of number 1? Superheated. So in order to look for S1, you have to go to table A4. In order to use table A4, you have to have two inputs. One of them has to be pressure. So they are P1, which is 10 bar, and a T1, which is 300 Celsius. And from the table, you can easily find entropy. So S1 is equal to 7.1214 kilojoule per kilogram per Kelvin. So now we're done with S1. After S1, we need to find S2G, which is our reference. How do we look for S2G? Again, we need to first identify what's the phase of point 2G. Point 2G is point G. So what do we know about point 2G? We know point 2G is on P2 line. So point 2G must have a pressure of 1.5 bar. If you start from pressure, you go to table A3. Pressure of point 2G is equal to P2, and it's given. It's 1.5 bar. Okay, from table, you can find S2F and S2G. Okay, even though I'm looking for S2G alone at this moment, I might as well write down many other properties. S2F is 1.4336. Do not forget a unit. And S2G is 7.2233. In addition to S, I also write down enthalpy, H2F and H2G. H2F is 467.11 kilojoule per kilogram, and H2G is 2693.6 kilojoule per kilogram. So now I have S1 and S2G. So which one is bigger? We can tell S2G is actually bigger. S1 is less than S2G. So where do you have to put number 1? Point 1 must be to the left of point 2G. So now let's go back to the diagram. Point 1 must be to the left of point 2G. So point 1 must be to the left of this reference line. Number 1 has to be somewhere here. And now you sketch 1 to 2s, you have to go straight down. Go straight down because it's isentropic. And this point will be your point 2s. And now you can see point 2s must be a mixture. Okay, and now I'm done with 1 to 2s. Next, I need to sketch 1 to 2. 1 to 2. What do we know about 1 to 2? 1 to 2 isn't the actual process. If it is an actual process, entropy always grows up. We proved this before. So if entropy becomes bigger, 1 to 2 must be going to the right because entropy is the x-coordinate. 1 to 2 must be to the right. Let's see if it is enough for us to fix point number 2. Let's go back to this diagram. 1 to 2 must go to the right. We know number 2 must be on P2 line. So can I actually put number 2 somewhere here? And then we connect 1 to 2. Is it to the right? Yes. If that's the case, number 2 will still be a mixture. Second option, can I put number 2 here, the same as point to G, and then when I connect 1 to 2, is it still to the right? Yes, but this time number 2 will be saturated vapor. Or option number 3, can I put number 3 somewhere here to the right side of the dome and on P2 line? And then when I connect 1 to 2, is it still to the right? Yes, but this time the face of the number 2 will be superheated. Again, 1 to 2 to the right alone is not enough for us to fix the location of number 2. You still have 3 possible solutions. Number 2 can be a mixture. Number 2 can be G point, and number 2 can be superheated. So how do we fix the location of number 2? Let's take a look. We have P2 and T2. Can we do the same thing as what we did for number 1? We start from 1.5 bar and find the corresponding saturated temperature and compare that to my actual temperature T2. Let's try that. We go to table A3 and we start from pressure P2, which is 1.5 bar. And from the table, we can find the saturated temperature we call Tsat2, and the value is 111.4 Celsius. What is our actual temperature T2? T2 is given as 200 Celsius, which is even higher than my saturated temperature. So what is our conclusion? Number 2 must be superheated. So now I can go back to my diagram and put number 2 somewhere to the right side of the vapor dome because it has to be superheated, and then connect 1 and 2 with a curve. Connect 1 and 2 with a curve. So that's it. 1, 2, 2. Skewed to the right, and number 2 has to be superheated on P2 line. So we've done the diagram 1, 2, 2 and 1, 2, 2s. Next part is to look for eta nozzle. Let's take a look. What is the definition of eta nozzle? It's defined as 1 over 2 V2 squared versus 1 over 2 V2s squared. Okay, so essentially we're looking for V2 and V2s. Which equation has velocity in it? Yes, first law. Okay, so now let's take a look at process 1 to 2 first. And we apply first law to this process. Because this is an control volume, so we have to use the long version. Q dot minus W dot CV plus M dot H1 plus 1 over 2 V1 squared plus GZ1 minus M dot H2 plus 1 over 2 V2 squared plus GZ2. Right hand side dE over dt. Steady state, right hand side goes to 0. And also because of steady state, there's no need for us to add a subscript to mass flow rate. And again, height does not change, so mgz1 minus mgz2, they cancel. And then, because the problem set is adiabatic, so there's no heat transfer. And again, this is a nozzle. A nozzle doesn't have any moving parts. If there's no moving parts, W dot CV goes to 0. Okay, so now we can rewrite this equation. Because we're looking for 1 over 2 V2 squared, so we move 1 over 2 V2 squared alone to the left-hand side. Right-hand side becomes H1 minus H2 plus 1 over 2 V1 squared. So now we can go back and rewrite the numerator. And then what about the denominator? We just repeat. For process 1 to 2s, we apply first law again. So similarly, you apply first law again. Your solution will be 1 over 2 V2s squared equal to H1 minus H2S plus 1 over 2 V1 squared. You can simply change the subscript 2 to 2S. That's it. So now we can plug in our new expressions back into the definition of efficiency. So eta nozzle this time can be rewritten to H1 minus H2 plus 1 over 2 V1 squared, H1 minus H2S plus 1 over 2 V1 squared. And V1 is given. What we need to do is to find H1, H2, and H2S. We just need to find those three enthalpies, and then we will be done. Okay, let's start from H1. Again, before you look for a property, you need to identify what's the phase. What is the phase of number 1? If you forgot, you can always go back to our diagram. Number 1 is to the right side of the vapor dome, so it is superheated. If it is superheated, you have to go to table A4. The two inputs we have for number 1, they are P1, 10 bar, and T1, 300 Celsius. And from the table, you can find H1 is equal to 3051.05 kilojoule per kilogram. This is how you find H1, very straightforward. Next, let's look for H2. How do we look for H2? Again, we need to first identify what's the phase of number 2. Let's go back to the diagram. Number 2 is to the right side of the vapor dome, so it must be superheated. So again, you need to go to table A4. To use table A4, we have to have two inputs. They are P2, 1.5 bar, and T2, 200 Celsius. From the table, you can easily find enthalpy. H2 is 2872.9 kilojoule per kilogram. So now we found H1 and H2. The only thing left is to find H2S. And again, the first thing you need to do is to identify the phase. Okay, what is the phase of point 2s? Let's take a look. Point 2s here is within the vapor dome. So point 2s is a mixture. If you look for the property of a mixture, what do you have to do? There's only one way to do it. If it is a mixture, you have to use this weighted average equation. Can you memorize this equation? Point 2s is mixture, so it has two components. They are saturated liquid, F point, and saturated vapor, G point. Okay, next one. How much vapor do we have? That's the definition of quality. And make sure you give the subscript 2s because that means this is the quality for point 2s. If you do not write a subscript, then people won't understand which point you are talking about. Okay, so make sure you give quality x a subscript. And then how much liquid do we have? That is the rest. So that's 1 minus x2s. Okay, let's take a look. Do we have H2F and H2G? Let's take a look. We actually found H2F and H2G from the table earlier. So we do have H2F and H2G. The only thing I don't have is quality X2S. If we can find a quality X2S, then we will be able to solve for H2S. How do we look for quality? We've done this a few times already. We just go to a different property. What is the property we will use? We will use the x coordinate, which is entropy. S2S. We know point 2s is a mixture. So how do you look for the entropy of a mixture? You do the same thing. Weighted average equation. S2F plus X2S times S2G this time. So now let's take a look. Do we have S2F and S2G? We actually found S2F and S2G earlier, so we do have those two. Next one, I don't have x2s. I don't have x2s. What about s2s? S2s. Let's take a look. 1 to 2s is a vertical line, so they must have the same x coordinate. And what is the x coordinate? S. So that means s1 must be equal to s2s. And do we have s2s, which is equal to s1? We found s1 earlier, so we actually have s2s. S2s is equal to S1, and we do have S1. So now take a look. One equation with only one unknown, we can easily find x2s. Okay, so now we perform algebra. X2s is equal to S2s minus S2f divided by S2g minus S2f. Okay, so you can memorize this format, which will make your calculation quicker in the future. It's actual minus f point divided by g point minus f point. And we know S2s is equal to S1. So now we plug in the numbers. Okay, all three numbers have the same unit, that is kilojoule per kilogram per Kelvin. It doesn't matter that kilojoule is not SI because they will cancel in the end. So the solution is 0.98 and quality does not have a unit. So now we can go back to the enthalpy equation. Let's take a look. Do we have everything now? Yes. So we can easily find H2S. What we do is just plug and chug. Okay, H2F and H2G. What is the unit for those two numbers? You can go back to our notes, and the unit we used is kilojoule per kilogram for both of them. So if you do not convert the units, that's okay. Just keep in mind your solution will have the same unit, which is kilojoule per kilogram. And from your calculator, you can find a solution for H2S is 2649.1. So now we have H1, H2, and H2S. Let's take a look. Go back to this efficiency equation. Do we have everything now? Yes, we do. So we plug in everything. Eta nozzle efficiency equal to H1 minus H2 plus 1 over 2 V1 squared divided by H1 minus H2S plus 1 over 2 V2 squared. Okay, so be very careful here when you plug in the numbers. Why? Make sure you use SI unit. H1 is 3051.05 kilojoule per kilogram, so multiply by 1000 to convert kilojoule to joule. And then do the same thing for H2. Plus 1 over 2 times V1 squared. V1 is given 30 meter per second SI unit already. And then we do the denominator. Okay, so now use your calculator. Your solution is 0.44. So the efficiency of the nozzle is 44%.